Right now, telescopes are collecting light from galaxies that are racing away from us faster than the speed of light. Their light still reaches us. And somehow, this breaks no laws of physics at all. How is that possible? To see it, we have to throw out almost everything intuition tells us about speed. Start with a rule everyone knows. Nothing can travel faster than light. That's true, but it's a rule about moving through space. It says a rocket, a photon, a signal, can't outrun light as it crosses the space between 2 points. It says a rocket, a photon, a signal can't outrun light as it crosses the space between 2 points. The expanding universe plays by a different rule. Space itself is stretching, everywhere, all at once, and the stretching of space is not something that has a speed limit. Here's how we measure it. The farther away a galaxy is, the faster it recedes, a relationship called Hubble's law. A galaxy 1 megaparsec away, about 3.26 million light-years, drifts away at roughly 70 kilometers per second. 1 twice as far recedes twice as fast, about 140. 3 times as far, 3 times as fast. Now just keep going. If every extra step of distance adds another 70 kilometers per second, then at some distance, the recession speed reaches the speed of light, nearly 300,000 kilometers per second. That distance is called the Hubble sphere, and it's simply the speed of light divided by the Hubble constant. For our universe, it sits about 14 billion light-years away. Every galaxy beyond that line is receding faster than light, and that's not a rare, exotic handful of galaxies. In our standard model of cosmology, any galaxy with a redshift greater than about 1.46 is already crossing that threshold. Most of the galaxies in the deep field images you've seen are on the far side of it. So the obvious question, if they're outrunning light, how does their light ever reach us? First, we need to fix a misconception. You've probably heard that a galaxy's redshift, the way its light gets stretched toward the red end of the spectrum, is like the pitch of a siren dropping as an ambulance speeds away. That's a Doppler shift, caused by something moving through space. The cosmological redshift is different. The light isn't stretched because the galaxy is speeding through space. It's stretched because space itself expanded while the light was in transit. A photon leaves a distant galaxy, and over billions of years the space it travels through swells, and the light wave stretches right along with it. This isn't just a nicer story. It's testable. If cosmological redshifts were ordinary Doppler shifts, distant supernovae would appear at specific brightnesses. If they come from expanding space, they'd appear at different ones. When astronomers measured type Ia supernovae, the special relativistic Doppler interpretation was ruled out at the 23 sigma confidence level. That's not a close call. It's one of the most decisive rejections in cosmology. Space really is stretching. Now the heart of the puzzle. A galaxy sits just beyond our Hubble sphere, receding faster than light. It sends a photon toward us. At first, that photon is losing ground. The space between us is expanding so fast that the photon is actually being carried away from us, even though it's aimed straight at our telescope. But here's the trick. The Hubble sphere is not fixed. Over cosmic time it grows, and as it grows, it can sweep outward past that struggling photon. Once the photon finds itself inside the Hubble sphere in a region where space is receding slower than light, it can finally make headway. From there it crosses the shrinking gap and lands in our telescope. So the light we see from these galaxies swam upstream for billions of years before the current turned in its favor. The Hubble sphere is not a wall, it's not an event horizon, redshift doesn't blow up to infinity there, and we routinely see straight through it. Which raises one more question. If we can see past the faster-than-light line, how far can we see? Consider the oldest light of all, the cosmic microwave background released just 380,000 years after the Big Bang, when the universe finally cooled enough to become transparent. It comes to us from a redshift of about 1100. The matter that emitted that light is now receding from us at about 3.2 times the speed of light, and when it first released that glow, it was receding at over 58 times light speed. We see it anyway. The true edge of what we can see is the particle horizon. The distance light has had time to cross since the beginning. Because space kept expanding while that light traveled, the objects that sent us their earliest light are now about 46.5 billion light-years away. That makes the observable universe roughly 93 billion light-years across, even though it's only 13.8 billion years old. But there's a bittersweet twist. Seeing something is not the same as reaching it. Dark energy is accelerating the expansion, and that sets a second, closer boundary. our cosmic event horizon, about 16 billion light-years out. Any galaxy beyond that, we can never travel to, never signal, not even at light speed. Roughly 97% of the galaxies we can currently see are already, in principle, beyond our reach forever. Their ancient light still arrives, but we could never catch up to them. So how can we see galaxies fleeing faster than light? Because faster than light here isn't motion through space. It's the stretching of space itself, which has no speed limit. Because light can be swept from a fast-expanding region into a slower one and finally reach us. And because the sky is a fossil record, we're not seeing where those galaxies are, but the light they released long ago, from a universe far smaller than the one we live in now. We're looking at a cosmos most of which we can never visit, glowing at us across a gap that only keeps widening.